Hello, everyone. I want to talk a little bit about chemical reactions and quantities in the chemical reaction process. And I'd like to give a few examples to start off with. So we're going to talk about reaction quantities. And in doing so, let's take an example that you're familiar with at this point and see if we can work through some sample problems to more familiarize you with all the details. In this case, what I want to start with is an example of the reaction between methane and oxygen to produce carbon dioxide and water. So in this case, what we want to do is if we had been given 3 moles, of methane, right? And we could ask the question, how many moles of water can be produced? And we should say how many moles of water can be produced from 3 moles of methane. Okay, so in this case, like all the others, what we need to do first of all is write a reaction. Now methane is CH4. It is the main component of natural gas. And it reacts with oxygen, which I'm sure you've seen, to result in the formation, certainly quite a bit of energy, and the production of carbon dioxide and water. All of these hydrocarbons always react with oxygen to produce carbon dioxide and water. So we have the discussion here to consider 3 moles of methane will produce how many moles of water, which we're looking at here. So the first thing we need to do is, if you will, step 1 is balance the reaction. So if we balance this reaction, then what we're looking at is this one will be balanced very quickly. It'll be CH4, put a 1 in front of it, and see that we need 2 oxygens. We could go through the process of organizing it, but I think you'll see it very quickly. 2 oxygen moles for every 1 methane mole produces the 1 mole of carbon dioxide, and of course 2 moles of water. Okay, so we have a relationship here of 1 mole of methane to 2 moles of water, but there's something to consider here. This is a simple case, but we'll walk through the same process in all of these. What you also want to consider here is, called step 2, create a pathway. For the calculations. And in this, what we really mean is something quite simple. We are starting with, in this case, 3 moles of methane, and we want to convert it to moles. Let me rephrase that. We're starting with moles of methane, and we want to convert it to moles of water. Now in this case, it's fairly straightforward because in the balanced reaction, we simply have this relationship that says for every 1 mole of methane, we're going to end up with 2 moles of water. So how many moles of methane do we have? Well, we have 3 moles of methane. That's what we're starting with. That's what our pathway tells us. 3 moles of methane. In this case, that's just over 1, just to keep things as a fraction. And in this case, we have a relationship that says, hey, we get 2 moles of water for every 1 mole of methane. So you can see very easily that moles of methane cancel, and that's simply going to yield 6 moles of water. Okay, that one was pretty straightforward. It wasn't too complex, but I think you can see the process. Let's take another example that we want to consider, and let's use the same reaction here. So if we said that we want to make 5 grams, so how many, let's put the question this way, how many grams of methane are needed to produce 5 grams of carbon dioxide. Now, this is a similar situation. I'm going to, of course, write the reaction again. This time I'll just skip right to the balanced equation. And, of course, what we have, a situation where we have methane, write the reaction as gas, plus 2 oxygen moles, of course, are going to yield 1 mole of carbon dioxide plus 2 moles of water. Now, everything is presented in the balanced equation always as moles, but what we're dealing with here is we want to know grams of these process components, so we need to have conversion factors. So let's take a look at what we need to understand. And we write a pathway, and the pathway says we're starting with 5 grams of carbon dioxide. So we're going from grams of carbon dioxide. We're going to need to convert that to moles of carbon dioxide. We're going to need to convert that to moles of methane, and convert that to grams of methane. Notice in this case we're going from the products to the reactants, but as you can see, the process is the same. Mathematically, they fit the same sequence. Okay, so let's put in all the necessary pieces. So we start off with 5 grams of carbon dioxide. So we have 5.00 grams of CO2. Okay, it's over 1. Now, we need to convert that to moles of carbon dioxide. So in order to do that, we say there's 1 mole of carbon dioxide for every 44.01 grams of carbon dioxide. And you can get that by adding up the atomic mass components of carbon dioxide for carbon and 2 for oxygen. So now we have moles, as you can see, of carbon dioxide. And we need to convert that to moles of methane, which is dependent upon the balanced equation. So we have 1 mole of methane for every 1 mole of carbon dioxide. from the balanced equation. And now we need to convert that into grams of methane. So to get that, we need to add up all the atomic mass units inside methane. So we have 16.04 grams of CH4 for 1 mole of CH4. So now we have all the pieces that we find necessary to complete this. And of course, you notice something here. Grams of CO2 cancel, moles of CO2 cancel, moles of CH4 cancel, and we're left with grams of CH4. And if we do the arithmetic here, it comes out to be something in the order of 1.82 grams of CH4. And again, we have accomplished a very similar process as the beginning, except this time we have produced it in the sense of grams. Okay, so for the next variation on this theme, we can also look at the amount of energy released in a reaction. Again, we're going to stay with the combustion of methane. So in this case, we could have a problem that reads something like this. Say, if the combustion of methane releases 891 kilojoules per mole of methane burned or methane used. How many kilojoules will be released when 20.0 grams of methane are reacted with oxygen? Well, the process is essentially the same as what we just completed. But now, instead of a product, we have an energy release. We can, first of all, consider this to be a product in the process. So let's write the equation again. We say we have 1 mole of CH4 gas reacting with 2 moles of O2 gas to result in the production of 1 mole of CO2 gas plus 2 moles of H2O as a liquid. And we say in this equation that the delta H, which stands for, in this case, the enthalpy or heat produced in this reaction, is minus 891 kilojoules. What that means is that we have a negative sign, which implies that we have released 891 kilojoules. We could think of it this way. We could say, we could write the same equation and say CH4, right, plus 2O2, right, yields 1 CO2 plus 2 H2O. And we could say, and it's on this side of the equation, it would be released. So we're releasing how much? 891 kilojoules. Because we have 1 mole here, that means we release 891 here. And think of this as the same way you would think of any of these other factors in the equation. Okay, so how are we going to set this up? Well, the pathway here is essentially the same way we set it up before. In this case, we're going from grams of CH4 to moles of CH4 to kilojoules. Okay, so in this case we have 20.00 grams of CH4, of course over 1, times 1 mole of CH4 per 16.04 grams of CH4. That converts it to moles of CH4. Now we're going to convert it to kilojoules, and we simply say 891 kilojoules are released for every 1 mole of CH4. And again, you see grams here cancel, moles here cancel, and we're left with 1,111 kilojoules are going to be released, or we would say the release, the delta H is equal to minus 1 kilojoules. All right, that gives us another process step to use in the reactions in which we're releasing energy. If we were absorbing energy, we could write it on the other side, and it would be a positive number, etc. Okay, so in this case, we have now calculated the release of energy based upon the balanced reaction. Okay, for this next sequence, I want to discuss with you the concept of percent yield. That means that we may run a reaction, but not everything works out perfectly, so we would have something less than 100% yield in a reaction. So let's take as an example a reaction, okay, between 50 grams of iron metal and an excess, in other words, more than enough, of sulfur. Result in the production of 41.26 grams of iron 3 sulfide and what we want to know is what was the percent yield. So again, we start off by writing the equation and balancing it. So we write the equation, we see that we have iron, Fe as a solid, plus sulfur as a solid, yields iron 3 sulfide, and that is going to be Fe2S3. That's a solid. It's also known as fool's gold because it looks like gold. And if we balance the reaction, we find that we need 2 of these to 3 of these to 1 of these. So the first step is write the reaction, balance the reaction. So again, we're going to follow the same pathway. Now, the pathway that we want to follow here is going to be, again, in the same format that we had before. We're starting with grams of iron. We're in need of going to grams for, in the end, of iron sulfide. But what we have to do is we have to go to moles of iron because the reaction is based on moles. And from that, we need to go to moles of Fe2S3, or iron 3 sulfide. And from that, of course, we need to go to grams of Fe2S3. So yield is always configured on the process of how many grams. Okay, so again, we follow the same process steps. So we started with 50.00 grams of iron, and that's over 1. Now we have to find out how many moles. Well, we can do that by multiplying this by the number that is 1 mole of iron is a total of 55.845 grams of iron. I got that off the periodic table. And of course now we have to find moles of iron sulfide. And notice that we have 1 mole of iron sulfide, iron 3 sulfide to be precise, for every 2 moles of iron. Okay? And then we need to figure out how many grams of iron sulfide that is, and if we add up all the pieces to iron sulfide formula, 2 parts of iron, 3 parts of sulfur, all as atomic mass units, we come up with 270.90 grams of iron 3 sulfide for every 1 mole of iron 3 sulfide. Now what this is going to give us, by the way, is what would happen with respect to a absolutely perfect reaction. In other words, 100% yield, because we need to know that before we can figure out what the actual yield was in terms of percent. So again, here you notice that the grams of iron cancel, the moles of iron cancel, the moles of iron sulfide cancel, and we're left with grams of iron sulfide, and it turns out to be a total of 121.27 grams of iron 3 sulfide produced. And this represents a total 100% yield. Perfect reaction. But we didn't have a perfect reaction. So what did we have? This also means this is the maximum, of course. The maximum possible. But we didn't get the maximum because in reality you very rarely, if ever, get a maximum that you could have because of the conditions of the physical structure of the reaction and other ancillary situations. So here what we obtained was 41.26 grams of iron 3 sulfide. And what we could have gotten under perfect situation would have been 121.27 grams of iron 3 sulfide. I say times 100% to give us a percentage that represents our actual yield, which would be 34.02% yield. And that gives us the current yield if we obtained 41.26 grams of iron 3 sulfide. Okay, for this next one, I would like to consider the concept that represents limiting reagent. In other words, as your book describes, we have one reagent that is in excess, we have more than we need, and the other reagent is not enough or limiting. A reaction can only occur to the best possible yield by using up the limiting reagent, and once that's done, the reaction is over. So we would have excess material left behind from the reaction that is going on in terms of its excess reactant. But let's talk about a specific example and go through this. Well, let's take a look at an unusual example here. Let's say that we had some chromium metal, and we're going to react it with iodine. Now it turns out if you react chromium metal with iodine, you can make what's called chromium 3 iodide. And if we do that, that's a solid. And we need to balance this reaction. So the balance of this reaction would be 2 of these, 3 of these, and 2 of these. Okay, so let's suppose that what we were given for this was 30 grams of chromium and 35 grams of iodine. And the question might be, which one is the limiting reagent? And of course, how much can we get of chromium 3 iodide. So the question might be, what is the limiting reagent? And what is the amount of CrI3 possible? That would be 100% yield. Okay, so we don't know whether this is the limiting reagent or this is the limiting reagent. The easiest way to do these, I think, your book gives you a couple of ways to do them. I think the second way is probably a lot simpler. Is to simply follow the process steps that we used earlier and solve this equation or problem twice. By solving it twice, once using the idea of 30 grams of chromium and the other using the idea of 35 grams of iodine, we're going to get two different values of chromium 3 iodide. Whichever is the smallest of the two is the reaction that would proceed based upon the limiting reagent, and by that very fact we then identify the limiting reagent. So let's set it up like we have before. Now, in this case, we actually have two pathways. We'll say pathway 1 simply goes like this, just like before. We have grams of chromium are to be converted to grams, to moles of chromium, which is then converted to moles of CrI3, which is then converted to grams of CrI3. The other pathway is in a similar vein, and that goes like this. Grams of iodine goes to moles of iodine, which then goes to moles of chromium 3 iodide, which then goes to grams of chromium 3 iodide. And now we have both setups. And remember, whichever produces the smallest number of grams of chromium 3 iodide is the limiting reagent. So let's start. I say we have 30.00 grams of chromium. That's over 1. And it turns out that 1 mole of chromium is actually 51.996 grams of chromium. That's off the periodic table. And in the balanced reaction, we have 2 moles of chromium for every 2 moles of chromium 3 iodide for every 2 moles of chromium. And with respect to the chromium 3 iodide, the molar mass here is 432.71 grams of chromium 3 iodide for every 1 mole of chromium 3 iodide. And now we can follow through the same sequence we had before. Grams of chromium cancel, moles of chromium cancel, moles of chromium 3 iodide cancel. We're left with grams of chromium 3 iodide, which is what we want. And this says we would end up with 249.66 grams of chromium 3 iodide. Okay, so we have one of them. So let's repeat the process. In this case, we have iodine, so we have 35.00 grams of I2. It's over 1. Now 1 mole of I2 is 253.81 grams. Okay, and we have 2 moles of CrI3, which is in the balanced reaction, to 3 moles. Let me make that clearer. This is CrI3. And this is 3 moles of I2 again from the balanced reaction. Again, the molar mass of chromium 3 iodide is 432.7 grams of chromium 3 iodide for 1 mole of chromium 3 iodide. And now, again, we go through the same process. Grams of iodide cancel, moles of iodine cancel, moles of chromium 3 iodide cancel. Well, again, we're left with grams of chromium 3 iodide. In this case, we have 39.78 grams of chromium 3 iodide. And obviously, this is the smallest amount, so this is the limiting reagent. This is actually pretty quick, because once you begin to set one up and you begin to set the other one up, you very quickly come to the conclusion of which one is going to result in the smallest number, sometimes even before you do the actual calculation. Okay.